So very good morning students. In today's class you are going to learn about the design of FAR filters using Hamming window. In the last two classes you have learned how to design an FAR filter using a rectangular window and Hamming window. In today's class we are going to do with the help of Hamming window. Okay. So let us see what is the problem statement they have given. Design the low pass digital filter to be used in an A to D H of Z D to A structure that will have minus 3 dB cutoff frequency at 30 pi radian per second and an attenuation of 50 dB at 45 pi radian per second. And the filter is required to have a linear phase and the system uses a sampling rate of 100 samples per second. So what are the data they have given us? You have a structure whereas initially you have analog to digital converter, then the filter which is represented by H of Z, the digital filter, followed by again the D to A converter, that is digital to analog converter. So in this particular structure you need to design the filter H of Z, okay, and the sampling frequency is also given and attenuation is also given. You need to design the low pass digital FIR filter, okay. So from the given data, first let us write what are the data given. So given is 3 dB cutoff frequency at the omega C as 30 pi radian per second and the sampling frequency is 100 samples per second. So from that you can calculate what is the omega 1 and omega 2. So the formula is the analog frequency divided by sampling frequency, 30 pi by 100, it is 0.3 pi, and omega 2 is 45 pi by 100, which is 0.45 pi radian per second. And based on the stop band attenuation we can calculate what is the window to be used, okay. Since the stop band attenuation is 50 dB, I can say that the Hamming window is having a stop band attenuation of 53 dB. So choosing the Hamming window will be the right one, and we got omega 1 and omega 2 also, right, and with that we'll be able to find out what is the value of n, okay. So for that already we discussed in the design procedure. We can obtain the value of n using the formula as n greater than or equal to k into 2 pi by delta omega, and k it is calculated as 4 and delta omega is given as the stop band attenuation. You can substitute and you can calculate what is the value of n. So whatever we are getting, you need to choose greater than that and see that it is going to be an odd number also. So substitute k is equal to 4 for the Hamming window and 2 pi by omega 2 minus omega 1 as 0.4 pi 5 pi minus 0.35 pi, which is n we are getting as 53.55, and as already I have told, n you have to select as an odd number and the next odd number is going to be 55. So n is taken as 55, and rest of the procedure it is the same as what we have done for the Hamming window and rectangular window. So once again I will repeat the procedure. You need to start with finding HD of omega. So what is HD of omega? Generally for a low pass filter it is e power of minus j omega tau, whereas modulus of omega less than or equal to omega c, and it is 0 otherwise, right. And as per the procedure, first you have to find HD of n using the inverse discrete Fourier transform formula as 1 by 2 pi integral of minus pi to pi HD of omega into e power of j omega n into d omega. So let us substitute what is HD of omega here and we'll simplify it, and after solving I am getting HD of n as sin omega c of n minus tau divided by pi into n minus tau for the case n not equal to tau, and if n is equal to tau, as usual how we had done it, we are getting as omega c by pi. And we know for the Hamming window the window function is represented as w of n is equal to 0.54 minus 0.46 cos 2 pi n by n minus 1. So using this let us list out all the values of Wn of n. And before listing out As the range of n is very high, I am not going to find the entire filter coefficient. Generally we will calculate. Okay, so as per the design procedure, h of n is going to be hd of n multiplied with w of n. Okay, so let us multiply hd of n with w of n for different values of n. And we have the equation as for n is equal to tau, that is for tau is equal to 27, we have sin omega c into n minus 27 divided by pi into n minus 27, and for n is equal to 27 it is going to be omega c by pi. And this after multiplying with w of n, we are getting this as h of n is equal to sin omega c of n minus 27 divided by pi into n minus 27 multiplied with 0.54 minus 0.46 cos 2 pi n divided by n minus 1, which is 55 minus 1, that is 54 for the case n not equal to 27. And for n is equal to 27, you just multiply omega c by pi into 0.54 minus 0.46 into cos 2 pi n divided by 54. So this h of n represents the impulse response of the low pass FIR filter. Okay, and since the range of n is very high, that is 0, 1, 2, 3 up to 54 you need to calculate. So instead of listing out all the values, generally I have written this h of n, which represents the impulse response of the filter. This is all about the design of the FIR filter using Hamming window. So we have another problem statement. Okay, the desired frequency response of a low pass filter is given. You need to design using Hamming window, and m is given as 7, and also you have to find the magnitude frequency response. And this I think you can do it as a homework problem. Please work out with the same procedure, and even the Hamming window, the window function is also specified in this sample problem. You can do it. Okay, once again let me specify what is the design procedure. First window, it is already specified, Hamming window, and n value is also given as 7, m is equal to 7, and to start with you have to find hd of n, and after finding hd of n for n is equal to tau and n not equal to tau, okay, and it will take the form sin 3 pi by 4 n minus 3 divided by pi into n minus 3 for n not equal to tau, which is tau is calculated as 3, and for n is equal to tau it seems to be 3 by 4. Then you just list out in the form of a table the hd of n for different values of n starting from 0 to 6, and parallelly you can have the Hamming window values. Then you multiply both the things to get h of n. And in order to obtain the frequency response, already we discussed, we have the formula for n is equal to odd. So use this particular formula and substitute h of n to get the magnitude frequency response of the FIR filter. Okay, thank you. Please work out this problem and see that you are able to get through. Okay, thank you. Thanks for watching. Let us continue in the next class. Thank you.